what distinguishes them? Well, we can rotate a rigid body. We cannot do that parity flip for a rigid body. So those subset of matrices with determinant equal to +1, we call them proper rotations. Those are rotations we could perform on a rigid body. The subset of matrices with determinant equal to -1, we would call them improper rotations. We cannot perform them on a rigid body. Now, if I take my matrix and I vary it continuously, oh, great. I feel much better. Okay. So if we take a look at this, how do I know that it's the matrix with theta equal to +1 that can be reached? Well, I know that if I was to set all of my parameters equal to 0, I would get the identity, right? So I'm considering smooth deformations away from the identity. And the identity as a determinant of A is equal to +1. So that's how I would know which of those two sets I have got. So let me tell you how you would get those elements with theta equal to -1. And you can try to convince yourself that this is true in general. So if you take a look at this matrix, so you've seen that matrix already. And we take that matrix, so let's call this A. You can check that A transpose A is equal to 1. And you can also check that the det of A is equal to -1. Now, my claim to you, so this is a nice thing to try to prove. You can look for a counterexample first, I guess, is to show that any A with det A equal to -1 can be written as 0, 1, 1, 0 times by a proper rotation. So multiplied by one of the rotations with theta equal to +1. You'll often see a picture drawn in textbooks which looks something like this. So there's two sheets, and this is now meant to be a picture of O2. The identity lives in one of these sheets, and by moving smoothly away from the identity, we can explore all of the elements sitting on this sheet. So this sheet itself forms a subgroup called SO2. If you look at the set of matrices with determinant A is equal to +1, that forms a subset. And if you check, does that subset satisfy the axiom of a group? Yes, it does. Another way of talking about this, we say that O2 is disconnected, and it has two disconnected components. So if you see any of this terminology, this is what people mean. Okay, so where did we start off? Well, our starting point was we said to ourselves, what would be good labels for a particle? And what we meant by that is, what observables would be invariant under a set of transformations I could consider? But I could consider almost the exact opposite of that question. So I could do the following. I could say, well, let me tell you what the good labels are. And why don't you tell me what the group of transformations are that will leave those labels invariant? That's a useful way to think in group theory. So it may be that in nature we've noticed something that stays constant, and we would now like to figure out what group of transformations would leave that particular thing constant. Okay. So let's start off with these examples over here. Let's consider a real vector with d components. So we will have some vector u with components I, and maybe some vector v with components I, and we will have a sum from I is equal to 1 to d. These are real vectors. And I may ask myself, well, what group of transformations leaves this set of this particular quantity unchanged? I'm going to write this in Dirac notation. Okay. Just remember, because we're dealing with real vectors, to get the bra from the ket, you just transpose. You don't take a complex conjugate. Everything is real. Okay. And our transformation that we will consider, set of transformations, will take vi into, so we'll have some sum. So I'm writing sums explicitly, but repeated indices are summed. Aij, vj. How would this transform? Well, if we look at uv, what would this turn into? So here, of course, this means that v goes into a times by v. And if I take the transpose of that equation to get the equation in terms of the bras, I would get v would go into v a transpose. Okay, so what would this go into? Well, this would go into u a transpose a v. And if this is really going to be invariant, well, this has to be equal to uv. I'm going to write uv in a slightly different way. I'm just going to write this as u times by the identity times by v. For which vectors u and v must this hold? This must hold for all vectors u and v. Because it holds for all vectors u and v, I know that this is not just a statement for a particular matrix element, it is a statement for all matrix elements. So I can take this equation and promote it to a matrix equation. And the matrix equation that I find out is A transpose is equal to 1. So here, in d dimensions, I've recovered the O2 example at the top there. So what is O2? O2 would be that group that would leave the inner product of two-dimensional vectors invariant. I could think of adding in one more invariant. And the next invariant that I could add would look like this. I take, in d dimensions, the completely antisymmetric tensor. So what properties does this guy have? If you swap two indices, any two indices, it picks up a minus sign. Okay? Once I've told you that, you know that if any two indices are the same on that tensor, this has to be equal to 0. And the only other piece of information I need to give you one value of the tensor. And then you can work out all others. Well, the value that I will give you is that epsilon 1, 2, 3, so on up to d is equal to plus 1. Now, another quantity that I could consider would be this. I'll take d vectors, and these indices are all summed. And now I say, I would also like this to be invariant. If I transform this, how does it transform? Well, this would turn into epsilon I1, I2, up to ID. I have got an IA1, J1, IA2, J2, ID, JD, contracted onto my vectors U, J1, V, J2, W, JD. So that's how it would transform. Each vector has picked up a factor of this matrix A. Now I want to study this object over here. What does this thing look like? Well, if I take I1, I2, up to ID, AI1, J1, AI2, J2, up to ID, JD. What I would like to do now is I'm going to relabel two indices. So what I call I1, I will now call I2. What I call I2, I will now call I1. So I can relabel dummy indices. This is epsilon I2, I1 up to ID. Then I would get A, I2, J1, A, I1, J2, going all the way up to A, ID, JD. This is equal to, I'm going to swap these two indices back. When I do that, it costs me a minus sign. minus epsilon I1, I2, ID. And I can swap these two around. I mean, these are just numbers. They're not matrices. They're actual matrix elements. I1, J2, AI2, J1. Everything else unchanged. So how is this related to this? Well, I swapped J1 and J2, and I picked up a minus sign. So what this tells me is this thing is completely antisymmetric in the indices J1, J2, up to JD. So once again, I only have to give you one value of it. The value that I will give you is this one. Epsilon I1, I2, up to ID, A, I1, 1. A, I2, 2. All the way up to A, ID, D. And if you go away and write this out, maybe you want to only do it for a 2 by 2 matrix, you can easily check for yourself that this is in fact just the determinant of A. So what we have here, this quantity over here, so let me clean that. I've now figured out what this coefficient was. So what is this equal to? This is equal to the determinant of A, epsilon J1, J2, up to JD, U J1, V J2, up to W JD. So if I require that both that is an invariant and this object is an invariant, now I've got SOD. Only those matrices with the determinant equal to +1, because that's the only way this would be invariant. Okay? So you can see that now we've turned the whole story on its head, and we've said that we started off and we said that we wanted labels that were invariant, and now we've seen that by stating what labels we would like to be invariant, we actually get a specification for what group we would like to look at. Are there any questions at this point? Yep.
The epsilon has lots of indices.
Yes.
Can you restrict them to about 3 indices for me to see what will happen?
Sure. You mean over here?
Epsilon 1 to 12 to say it was +1.
Yes.
That's too long for me.
Okay.
Can you shorten it? And then
Sure. Would you like me to redo this argument with 3 indices?
Yeah, something like
Sure. Okay. So what we are saying is we want this to be true. Sum from I is equal to 1 to 3 of ui vi. That's one thing that I don't want to change under my transformation. Okay? And if we just ask that this doesn't change, we've already figured out that that means that A transpose A must be equal to 1. But now I want to put in an extra condition. I also want epsilon I1, I2, I3, ui1, vi2, wi3. I also want that to be invariant for any 3 vectors u, v, and w. Okay? So let's see how this thing would change. Well, I know what I should do. So, for example, if I was looking at the w, the v, sorry, I know that vi2 would turn into ai2, j2, v, j2. And these indices are summed, okay? It would just pick up a factor of a up front